Hello student, welcome back to lecture series on Z transform. For more videos, you can check in my I button here. So you'll get the complete playlist there, or you can check in my description box. So down there description box, you will get the complete playlist on linear differential equation with a constant coefficient, Z transform, Z after Fourier transform, Fourier sine, cosine, and their inverse transform. Okay, yes. So without further ado, let's get dive into our today's lecture. So in my today's lecture, I'm gonna explain to you all, find out the Z transform of Z transform for sine k pi by 2 plus alpha. Similar example result I explained in my previous lecture. Okay, now let's get started our today's solution. Now see that, as we know that the result for finding the Z transform for sine alpha k cos alpha k already we learn. Okay, so let me write that result, so it will be way better for solving the example. Okay, yes, the Z transform for sine alpha k. Okay, let me write Z transform for sine alpha k. Okay, Z transform for sine alpha k when k greater or equal 0, and Z transform for cos alpha k. Okay, Z transform for cos alpha k when k greater or equal 0. Okay, so we know that both of these are having denominator same. Okay, but only the numerator are changed. Okay, yes, so sine alpha k has a numerator Z sine alpha. Okay, Z sine alpha. Okay, numerator Z sine alpha, and cos alpha k having numerator Z into Z minus cos alpha, Z into Z minus cos alpha. Okay, and both are having same denominators. Okay, what is the denominator? Z square minus 2Z cos alpha plus 1. Okay, Z square minus 2Z cos alpha plus 1. So Z square minus 2Z cos alpha plus 1. Okay, and modulus of Z which greater than 1. Okay, yes, here it is also modulus of Z greater than 1. Okay, these are the two important results, guys, you need to know. Okay, these are useful here for finding the Z transform for the sine of k pi by 2 plus alpha. Okay, yes, now see that, as we have observe it carefully, as we have sine alpha k, it seems like that we have the only single term present here. Okay, only single term present here, but in our example we have given sine of two terms, a plus b. Okay, so for that what we need to do? Okay, for that we need to apply sine a plus b result here. Okay, and we know that sine a plus b can be written as, okay, let me write sine of a plus b first here. This one is also important result, sine of a plus b. Okay, sine a cos b plus cos a sine b. Okay, sine of a plus b can be written as sine a cos b plus cos a sine b. Okay, yes, so let's apply this Z transform over here. Okay, sine of k into pi by 2 plus alpha, okay, can be written as sine a cos b. Okay, sine k pi by 2 cos alpha. Okay, sine k pi by 2 cos alpha plus cos k pi by 2 sine alpha. Okay, don't get confused, guys, just I need to replace the value. A, it is k pi by 2, b, it is alpha, replace all over here. Okay, so replace enter this value here in our Z transform. Okay, and we apply linearity property for Z transform. And what is the linearity property? It says that wherever you get the constant term, take it outside, and inside go for the Z transform. So cos alpha, it is a constant here, take it outside, find out the Z transform of sine k pi by 2. Okay, sine alpha, take it outside, Z transform of cos k pi by 2. Okay, yes, let's go for the next step. I'm going to write this step like a cos alpha outside, as it is a constant term, Z transform of sine k pi by 2. Okay, yes, plus sine alpha outside, Z transform of cos of k pi by 2. Okay, this one is the Z transform for these two terms. Okay, and a constant term I taken it outside over here. Okay, yes, and we have the k. What is the condition for k? K it is greater or equal 0. So we apply these two results. Okay. Now what we do? Put the values over here. Put these values over here. Okay. Yes. So cos alpha. Okay. So what is the alpha? See that. What we have alpha? So we have to cos alpha, it is constant here. Okay. So keep it as it is. We are not going to do any changes here. Okay. So cos alpha as it is here. Z transform of k pi by 2. Okay. So that means we have sine of k alpha. Okay. Sine of k alpha. So we have another similar term compared here. Okay. So k pi by 2. Compare with the alpha k. So what is the alpha? Alpha it is a pi by 2. So replace pi by 2 here, replace pi by 2 here. Similarly alpha it is a pi by 2. Replace pi by 2 here, pi by 2 here. Cos alpha k apply it here, sin alpha k apply it here. Okay. It is way easier. Don't have anything difficult guys. No need to get confused. Okay. So what we have here, sin k alpha and cos k alpha. So okay, that we needed here. So in this case alpha is a pi by 2, in this case alpha is a pi by 2. So sin z transform needed alpha pi by 2 and cos z transform which also needed alpha pi by 2. Okay, replace both of these values in our z transform. Okay, z transform is sin k pi by 2. Okay, so it can be written as z sin pi by 2. Okay, upon z square minus 2z cos pi by 2 plus 1. Okay, so I'm writing here for this value z sin pi by 2, z sin pi by 2 upon z square minus 2z, z square minus 2z cos pi by 2 plus 1. Okay, this one is a bracket complete. I written this z transform of this term over here plus sin alpha under bracket cos k pi by 2, cos k pi by 2. Okay, so alpha is a pi by 2 here. So replace z into under bracket z minus. Okay, z into z minus. What we have? Cos alpha. So cos pi by 2. Okay, upon completely divided by z square minus 2z cos pi by 2, 2z cos pi by 2. Okay, plus 1. This one is the value I replace here. Okay, so you all need to know that cos pi by 2 and sin pi by 2. Okay, when cos pi by 2 1, cos pi by 2 0, sin pi by 2 gives us the 1. Okay, so we have sin pi by 2 which is 1 and cos pi by 2. On y axis we have cos 0 and y on imaginary axis we have sin 1. Okay, so we are going to replace these values over here. Okay, sin pi by 2 is 1, cos pi by 2 is 0. So if it is a 0, that means this entire term gives us the value 0, this entire term gives us the value 0. Okay, so cos alpha under bracket remain z square plus 1 as a denominator here, z square plus 1 denominator. Sin pi by 2 it is 1, so it numerator it is only z. Okay, this bracket complete. Sin alpha. Okay, sin alpha. So cos pi by 2 it is a 0. Okay, cos pi by 2 0. This gives us the 0. Z into z, we write as z square. Total divided by, okay, total divided by z square minus cos pi by 2. Cos pi by 2 what it is here? 0 plus 1. Okay, so we write z square plus 1. This one is the bracket complete. Okay, now see that I written this as a simplified form. Okay, now what we do, we take a denominator common. Okay, try to simplify term, or you can keep that one as it is. Okay, this one may be your required answer. Okay, but let me write one more step that you can also understand how can we simplify the steps. Okay, z square plus 1 keep 1 times as a denominator. Okay, numerator z cos alpha plus z square sin alpha, z square sin alpha. Okay, this one is a z transform. Okay, this one is a z transform for z sin k pi by 2 plus alpha when k greater or equal 0. See that guys, it is very easier, easy solution. I hope you all have understood my entire solution. Okay, I applied here the z transform of sin alpha k and cos alpha k. One of the result for sin a plus b, which is sin a cos b plus cos a sin b. After that I replace the result for sin alpha k. Okay, cos alpha k over here, applied for linearity property for z transformation, and I received here the final answer here. Okay, I hope you all have understood this entire solution guys. I want you to take some example for your homework. Okay, yes, complete this example for your homework and you can comment me answer in my comment section. Okay, So answer it is quite difficult to comment, but you can post me photo also in my comment section. Okay, yes. So example, take this example for your homework. Okay, yes, z sine hyperbolic. So we already learned the result for hyperbolic function. Okay, z sine hyperbolic k pi by 2. Okay, z sine hyperbolic k pi by 2 and k greater equal 0. Okay, consider this example for your homework. Okay, yes, take one more example, z cos hyperbolic k pi by 2. Okay, z cos hyperbolic k pi by 2. Okay, take these two examples for your homework. Okay, these are the easy examples already I explained here for z transform and z transform and sine hyperbolic, cos hyperbolic, or sine cos z transform here in my last lecture. Okay, yes, so it is very easier guys, not the difficult. You can easily solve these examples. If you don't know the result, let me explain. Sine hyperbolic can be written as sine hyperbolic alpha k. It is only hyperbolic replace here and hyperbolic replace here, so it only the value come sine hyperbolic alpha k, cos hyperbolic alpha k, and cos. Similarly for cos alpha k, cos hyperbolic alpha k, we can write cos hyperbolic alpha k upon cos hyperbolic alpha k. Okay, this is only hyperbolic replaced here, otherwise all the form it remains same. A modulus of z greater than 1, that condition get replaced. Okay, with exponential term. Okay, I hope you all have understood guys. This is my today's lecture. Complete this example for your homework and tell me the answers. Okay, so that's it here for our today's lecture. We go for next some more example in our next lecture. Okay, so I hope you all have understood everything here in my today's lecture. So thank you everyone. Thank you for my today's lecture.